My name is Larry Lapides. I'm with Imperas Software. I'll be talking today about RISC-V processor verification. So the topic today, the reason why we're talking about verification is that with all due respect to MIPS and Andes and the other processor IP vendors, a number of people in the RISC-V community are building their own RISC-V processor. And if you're building your own processor, you actually need to verify that processor because it's going to go in silicon and people are going to use it and depend on it. So what we're seeing here, though, is that there's a bit of a disconnect in RISC-V. And what is this RISC-V disconnect? Well, what we have is the users that are expecting quality to be the same as ARM. But we have developers that don't have the resources that ARM has. You know, ARM runs something like 10 to the 15th verification cycles on a core, which is, I don't know, 10,000 simulators running continuously for a year. So that's quite a bit of verification power. RISC-V, what we're seeing is actually the processors might not have all the features that ARM has, but a lot of those features are legacy features. And what companies are doing with RISC-V is taking exactly the feature set they need. What we're trying to do with those companies is to provide the verification tools so that they can build a quality RISC-V processor. So I'll talk today about verification plan, about methodology choices, the key technical pieces, and then some results and summarize. And I'll try and get through this in 15 minutes. The slides are available. I'm happy to send them to you, but we might go a little quickly here. So let's start with the verification plan. So the verification plan is sort of an obvious starting point, but also often neglected. What we see in the industry is that processor verification is actually 5 times harder, more or less, than SoC verification. You use a 5-to-1 ratio of verification engineers to design engineers. So you ought to do some planning so that you use these resources efficiently. So the verification plan needs to cover metrics, needs to deal with resources and methodology. So that's a starting point for verification. Methodology choices are interesting here. And we see here that there are basically 5 different levels of RISC-V processor DV methodology. So starting with just getting something running and you get hello world working. So this is starting with your RTL description, system verilog, you can actually run hello world. Great. You can then go to self-checking test, post-simulation, trace log file compare, and then different step and compare, synchronous, and then an asynchronous continuous compare. Really what we see used are just 2 methods. One is the post-simulation trace log file compare, and the other is the asynchronous continuous compare. So let's hit these. So this is the post-simulation trace log file compare. Yeah. So what we have here is tests feeding into both the RTL and the reference model. And then you're running those tests through both, get a log file out from both, and you do a comparison of the log file. Fairly straightforward, fairly obvious thing to do. And the key pieces of this are the instruction set simulator that serves as the reference model, that's the ISS, and then the instruction stream generator, the test stimulus generator, the ISG. And typically that's going to be something open source like the Google RISC-V DV instruction set simulator or instruction set generator. On the ISS side, Imperas has a free instruction set simulator as a reference model. That's the RISC-V OVP Sim Plus. That's an easy thing to use. We actually have hundreds of users for that. Well, hundreds. We have more than 100 users for that. Shouldn't exaggerate too much. The issue with post-simulation trace compare is that if you have asynchronous events, if you have interrupts, if you're using debug mode, privilege mode, things like that, then this doesn't really cover those. So that's where the asynchronous continuous compare comes in. And here, what you're doing is effectively something very similar to a step and compare, but they're not running quite in lockstep because the reference model needs to understand those asynchronous events and how the RTL is dealing with those. And this asynchronous continuous compare methodology is the methodology that's needed to support features such as interrupts, such as privilege modes and debug mode, and the multi-heart or multi-core processors, multi-issue and out-of-order pipeline. So as you get to any sort of processor complexity, really this sort of methodology is what is needed. So methodology, that's good. You've got those two choices. Often people are using both, or they're starting with one, starting with the trace compare and then moving to the other as they move further on in the verification task process. So let's look at the key technical pieces now of that asynchronous continuous compare. So this is just a block diagram. Let's fill in some of these pieces here. We'll start with a reference model. There's verification IP here. There's the RISC-V verification interface, so a standard interface for the test bench to talk to the reference model. There's functional coverage modules. There's the test stimuli. Last but not least, you actually have to have RTL, a device under test. And a key piece of that is this tracer here. The tracer is not the implementation of the hardware tracer. It's actually more of a monitor on the RTL that gets the right information into the reference model. So let's do a quick pass through these key components. First is the reference model. So the reference model needs to support the full RISC-V specification. That's what we're showing here. Imperas has built this base model. The base model supports the full specification, everything that is stable, so not just ratified, but everything stable. And this is configurable then to any of the extensions in RISC-V and to any version of that extension. Now, I should read my other notes here. Sorry, let's see. So a couple of other things here. The base model is built using a test-driven development methodology. So we're writing tests as we add features to the model. That's important for a high-quality model. You're not going to get high-quality RTL without a high-quality model. And then the APIs that are used for building the model have been refined over the last 15 years and over more than 15 different instruction set architectures. So we support well more than RISC-V. Right now, that's our focus. With RISC-V, you're going to be adding custom instructions. That's the beauty of RISC-V. Everybody wants to do something custom. That's the great thing. If you want something standard, go with ARM. You've got standard cores. There's no risk to that. Everybody knows ARM works. But with RISC-V, you're going to do something custom. So that's what this piece is here. It's an external library, an extension library for adding those custom pieces. We can build that. Customers can build that. It's the same APIs that are used on the base model. So what happens is that when the base model and the extensions are put together, to the tool set, it looks like just one model. They don't see any difference there. And so all the tools work with that extended model. There's verification IP that is part of the verification environment. This is for moving data from the system Verilog RTL into the reference model. It formats the data, allows us to do functional coverage, as well as doing the verification compares. And then in the C piece of the reference model, we're doing other things like understanding what the asynchronous events are. And specifically, there's a predictive engine. So what we're doing when an asynchronous event happens, we're looking at the potential legal outcomes from that asynchronous event, watching, monitoring the RTL, making sure that one of those legal outcomes happens from that asynchronous event. RVVI is a standard interface that we've developed together with our partners and customers. It just means there's an open standard for moving data from System Verilog to the C reference model. Functional coverage is a key metric. I started in the verification industry more than 20 years ago, and actually the company I was at then was a company that pioneered functional verification or functional coverage for RTL. I've seen the value here. It's especially important with the complexity of a processor. So what we're doing here at Imperas is providing basic functional coverage modules in System Verilog, covers all of the instructions, and then it's source code, so you can go add to that for whatever you're building, and then that functional coverage information can be integrated in with whatever verification tools you're using. For example, in this case, the Synopsys VCS and Verdi environment for System Verilog. And then last is test stimuli. Test stimuli can be either the instruction stream generator, constrained random, in which case functional coverage is really important because otherwise how do you know what you've actually tested? And then the other piece of test stimuli are directed tests. And we have two types of directed tests here. One are the architectural validation tests. We've built some of those. There's some from RISC-V International. Then there are also some more robust tests specifically for the vector extensions and PMP. So tests, those are a key thing. One other thing I'll add here is debug. Debug is important when you're looking at a complex device like a processor, trying to figure out where the failure was. And so as we're working with these different System Verilog simulators, the integration that we've developed enables co-debug. So here actually you can see the Cadence waveform viewer in their debug environment, and then the Imperas debug environment. So you can look at the test and what the reference model is doing in the Imperas environment simultaneously with what the RTL is doing, gives you that co-debug environment that's key. Results. There are a number of companies that are using Imperas technology. Open Hardware Group and their member companies is one. Their version of that asynchronous continuous compare flow is shown there. This is actually a third generation verification flow with Open Hardware. The CV32E40P has taped out in a number of different SoCs with Silicon Labs and other companies. And then right now there are 4 other cores in flight at Open Hardware using this methodology that expect to complete verification by the end of this year. And then other successful DV projects are shown here. And yeah, there are some companies using Imperas. So, summing up, I wanted to just give another view of the customers and partners. We do have a large number of customers and partners. We do support the processor IP vendors. It's not all about people doing their own RISC-V, but we also support Andes and Sci-Fi, MIPS, Open Hardware, NSI Text, Codasip. So we support those folks. There are a number of customers. But then that free RISC-V OVP Sim Plus, there are more than 100 different organizations that are using Imperas. And it makes for a nice slide with a bunch of logos, so this is a good thing. There are also universities that are using Imperas. Getting back to the beginning, what we're trying to do is solve that disconnect in the verification side. And so we see that verification is going to be the key to success for these RISC-V projects. And with that, the processor DV, the processor verification methodology, has been evolved by Imperas together with our customers and partners. In these projects, the tool costs are going to be small compared with the engineering resource cost. You're going to use a lot of manpower on verification. There's just no way to get around that. We see with our customer base that successful experience management teams are aware of this and they're executing on this right now. Imperas DV solutions provide the products to accelerate building a robust DV environment. So, thank you. I'm Larry. I'm here. I can answer questions for you now. Our stand is just right back there. So, thank you for your time.